Okay. So today's the continuing the previous videos. I will talk about some baryogenesis. In the previous video, we discussed the number density and energy densities in the equilibrium thermodynamics of the early universe. So there are some of the reviews on the some number density, energy density, and antropological density table for each cases. The relativistic and the boson and fermion case, and the non-relativistic and the non-zeros chemical potential. So there are some number densities are given. For the fermion case, there are additional factors. For the non-zero chemical potentials, this gives the asymmetry between the particle and the antiparticle. By using the such a formula, we can measure the baryon asymmetry and the Lapton asymmetry. For the baryon asymmetry, it can be measured by the Big Bang nuclear synthesis. There are many kinds of the nucleons, and we can measure the eta B quantity baryon to the photon light year, and there are also other parameters like the delta B, which is a baryon to entropy light year. The lepton asymmetry also can be obtained by the non-zeros chemical potentials of the lepton or neutrino field. There are a large discrepancy between the baryon and the lepton asymmetry for that given at L. So today, we focused on some real number violation, B violation. How can we make such a baryon number violations in the standard model or beyond standard model? And before that, we'll focus on the some topological soliton because there are one way to make the baryon number violation the instantaneous parallel. So the instanton is some specific classic solutions of the given system. There are some of the such a form of substantial. There are two degenerate vacuum, and we can assign the index small n to the each vacuum and equal to 0 and equal to 1. And the instanton is a tunneling solutions between the such a degenerate vacuum. So for simplicity, first of all, we consider 1D model with the spatial with the time homogeneity. So there are no time dependence. And the Lagrangians are just given by the kinetic terms and the potential term. And because this is a 1D, we cannot decompose it in the space-time derivative. And the equational motions are just given by the such a form. And by using this equational motion, we can find the Hamiltonian density and the energy. And we want to make the finite energy solutions from the equation motion and energy formula. To do that, at the spatial infinity, the field value should be located in the zeros of the potential, the vacuum of the potential. That is conditions for the convergence of this integral for the energy. So we should assign each spatial homogeneity to the degenerate vacuum. For example, if there's a potentials given by the three degenerate vacuums with the local minimum pi 1, pi 2, pi 3, then there are several possible solutions, especially the non-trivial solution. At the spatial homogeneity, this is a 1D model, so there are minus infinity and x equal to the infinities. There are two spatial infinity, and at the x equal to minus infinity, the field values of pi can be located in the pi 1, pi 2, and pi 3. But the x equal to the infinities, there's such field values can be changes. For example, the solution 1 at x equal to minus infinity, pi is equal to pi 1, but the x equal to the infinity, pi equal to pi 2. So these solutions that correspond to the tunneling from the pi 1 at the minus infinity to the pi 2, x equal to this infinity. And there are also the possible solution 2, 3, and 4. So it requires that the degenerate vacuum size for the finite energy solutions to obtain the non-trivial behaviors. So this is an important point. There should be the degenerate vacuum state, and the spatial infinities assigned the degenerate vacuum to have the finite energy solutions. To be specific, there are some detailed calculations that if there are two vacuums in the potential, The potential U is given by this form, while the vacuums are given by the m over the root lambda. And the equational motions are following, and we can find some of the solutions x in terms of sort of the field values and the potential. So the solutions are given by the such a hypertangent form. So at the x equal to the minus infinity and x equal to the infinity, there are two solutions. There's the minus infinity and infinity, and the two vacuums are assigned to the pi minus and pi plus. And when the x equal to minus infinity, pi equal to pi minus, and the x equal to infinity, pi equal to pi plus is called a kink. So it can be drawn by the such a diagram. At the x minus infinity pi minus, and at the x equal to 0, there is the boundary between the two vacuums area, pi minus and pi plus, and this is called the domain wall or the kink. And conversely, if the pi plus at the minus infinity and the pi minus at the infinity is called the anti-kink. And we can also confirm that the energy density is actually the finite. The energy density as the spatial infinity is extremely small, so the integrations that converges for the energy. So this is some of the reason of the topological solutions, but why we call that this is a topological and a soliton. The topological mean that such a assignment between the spatial infinity and the degenerate vacuums are classified topologically. That's a very important point. I will repeat it again. And the solitons means that there are no dispersions. So the energy densities gathered in the locally. We already saw it in the previous slide. We will talk about some of why the topologies are somewhat very simplest here. So there are some of the spontaneous symmetry breakings that exist in the such a topological solution. So for high energies, the symmetries are given by the group C, and it is spontaneously broken to the unbroken symmetries subgroups H. Then the quotient groups G over H is the correspond to the degenerate vacuum. So it can be shown by that. So consider there are some of the vacuums pi 0. And such as spontaneous symmetry breaking mean that the vacuums is not invariant under the transformation. So if there's some small h's, there's the elements of sort of the unbroken symmetries, capital H's, then the such a vacuum stays invariance under the such as elements of the small h's. But if the small g is not elements of the unbroken symmetry groups, capital H's, then such a small g changes the vacuum. So the vacuums that are not invariant. So there are some of the degenerate vacuums that exist. And if the g acts on some specific vacuum, then this make we just difference vacuum, so pi choose prime. So we can cite that the cosat from this capital H is unbroken symmetry, H is and G1, H, G2, H is correspond to the degenerate vacuum, each vacuum. So the collection of the such a cosats that correspond to the quotient group, so that this G over the H is the degenerate vacuum. So we can represent this degenerate vacuums as the quotient group G over the H's. And in the previous slide, we should assign the spatial infinities to the degenerate vacuum. And this can be classified topologically. The spatial infinities and the n-dimensional space-time, this can be represented by the Sn. So there is the isomorphic mapping between the spatial infinities and this n-dimensional sphere. For example, 1D, there is x equal to minus and infinity, and this can be correspond to the S spheres, and R go to the infinity, which the 2D, this is corresponds to just circle. And in the 3D, there is the R go to the infinity, this corresponds to the sphere. So the point is that we should assign between the spatial infinity as n and the vacuum G of the ITs. And such a mapping can be classified by the ant homotopy groups, which is denoted by the pi n of the G over H. This pi n of the specific manifold X is that defines as like that. There are some of the loop is a mapping from the space X to the n-dimensional sphere, and we can classify the such a loop as some of the cosine. And if the such a manifold X or geometry H is given by the n-dimensional sphere for the n-homotopy group, then pi n of Sn equal to the integer z. And for spatial dimensional d, the n are given by the d minus 1. So we already saw that there are one-dimensional topological soliton, which is a kink, and we will see that the additional the kinds of the topological soliton in the high dimensional, like as the Vortex, Monopole, and Instanton. And today we will just show that to the by this Instanton, and maybe the next videos will focus on some of the more detail in the Instanton on this polygon. So let me saw that equal to 1. In that equal to 1, there are some G2 symmetry before that the spontaneous symmetry breaking. This is a discrete symmetry. And after the spontaneous symmetry breaking, SSB, there are no remain symmetry. There are just identity transformations that are in the subgroup. So the degenerate vacuums are given by the G2 over the 1, and the zeroth homotopy groups of this G2 of the ones are given by just the G2. So there are just a plus and a minus, and it is correspond to kink and anti-kink. So this can be the represented again. So that there are partial infinities minus infinity. This corresponds to the S0, and this is represented as this index 0. And there are degenerate vacuum pi minus pi plus. This corresponds to this G2 of the 1. So there are minus pluses, and we can assign the each spatial infinity to the different vacuum minus pi plus. This corresponds to the kink, and for the minus and infinity, so we can swap the vacuums to the pi plus and pi minus. This is correspond to the anti-kink. So this is called the kink, or called the domain monster in the universe or cosmology. For the d equal to 2 dimension, there's appears the kink. In this case, before that broken symmetry, the symmetry is given by the U1 with such a potential, but after the SSB, there are no remain symmetry. The spatial infinity is the S1 circle at the R equal to the infinity in the 2 dimensions. So this is represented in the index 1, and there are the vacuum U1 sort of the 1, and U1 sort of the ones are such things, such a manifold is isomorphic to the S1. So the pi ones of the S1s that are the actually the group of the integer z. So there are some of the minus 1, 0, 1, 2, 3, 4, such winding numbers are assigned, and that these winding numbers are classified the vortex topologically. So there are spatial infinity S1, and the degenerate vacuum U1 over the 1. And each winding numbers represents how much the rotated for the one cycle of the spatial infinity. So we can assign that there are 0.1, 0.1, 0.2, and 0.2, but the winding number 2, there are 2 cycles for the spatial infinities for the vacuum. There are some of the continuous conditions for this loop for the anthropomorphic groups, and such a vortex is often called the cosmic swings in the cosmology scheme. So there are only the 2 things that remain, but I will talk about these in the next video. There are 3D dimensionals is called the monopole or magnetic monopole. So the spatial infinity is S2, and the original symmetry is given by the SO3, is represented by the ball, and after the SSB, the remains unbroken symmetry is U1. This is represented by the radius with the pi. So the degenerate vacuum is the SO3 over the U1, which is isomorphic to S2. So the pi shape of S2 is the isomorphic to the Z. So this is the also the winding number or pole triangle index, which is classified the Marati monopoles topologically. So today we saw the topological soliton that can be classified topologically by the mappings between the spatial infinities and the degenerate vacuum. This can be classified anthomorphic group. And such assignment or mapping between the spatial infinities and degenerate vacuums for the finite-energy solutions.